Hello and welcome to a review of electrical fundamentals and Ohm's law. Serves for a couple of my classes, audio electronics and probably speaker systems. This review assumes you've already learned this material in previous courses, but maybe you've had a semester or two without it and you need it to proceed onward in this class. All right. I'll just review the basics, what the difference is between voltage, current, resistance, and power, define and differentiate them, and review Ohm's and Joule's laws. Also key in this is kind of recognizing the different representative symbols, the letters that are used in the equations and all that. All right, so let's start with the obvious one, voltage. Voltage is electrical pressure. It's the desire for charge to move from one location to another. When there are more or less electrons on a surface or on an object, it negatively charges it. And the more negatively charged it is, the more voltage there is, the more potential there is between that object and another object that has less or more electrons. Voltage measures the potential to do work. It's the potential to move charge because of that difference, because those electrons really want to go back home. They really want to go to a place of equilibrium where there's an equal number of protons and electrons on a surface. So we measure voltage. We measure potential in voltage, and we label it with either the letter V or E. E is kind of the old school way of doing it, but you will definitely see voltage measured in V rather frequently in equations. And if you really want to memorize it, it's the voltage is that pressure. It's how desirous charge is to want to move from one place to another. So in the water metaphor, we typically think of voltage as pressure behind the movement of current, which is in the water metaphor the actual movement of water. So voltage is the pressure of water. Moving to white here, these are whiteboard notes. These are things that you should know in order to do basic Ohm's law calculations in my classes. What is the phenomenon here? It's potential or electromotive force. What's the water analogy for voltage? It's pressure, water pressure, if you want to think in terms of water. The letter E is the typical term used to define it, but our units are volts and voltage in volts, and the symbols you'll see in equations are V and E. Cool. I mentioned current a second ago. Current is the actual flow of charge. Voltage, of course, is the pressure to move that current, but current is the actual flow of charge. Technically, it's not really the flow of electrons, it's the flow of charge. That's too big of a concept to talk about in this review, but for the analogy purposes, let's just think of current as the flow of charge, and it, of course, is conducted through the movement of electrons. But we measure current, how much charge is flowing, in amperes or amps. An amp is a flow of 1 coulomb. A coulomb is a measurement of charge. It's quite a lot of electrons, 6.25 billion electrons moving per second. 1 amp is a probably rather large amount. And current is symbolized as A or I. I is the more traditional way of doing it. But when we start measuring amps, we typically will interchange A and I all the time, which if we go to our whiteboard notes, you'll see it here in blue. Current is the flow of charge, and it is the letter I, and our units will be amperage or amperes or amps, and the symbol, of course, is A. Now, if you've studied the Ohm's law before, you know that the flow of charge, that current, is inversely proportional to its resistance. That's Ohm's law. And resistance is that opposition to the flow of charge. So you've got pressure, voltage, pushing on electrons, pushing on charge to move. And then you have resistance pushing against that. And the net result, of course, when those two interact, is the amount of current. So resistance, if we were to think in terms of the water analogy, it would be the size of pipe, the size of conductor, the length of it, and this would impact how able charge is to move. This is the same thing with wire, how conductive a wire is, how thick it is, how long it is. So The thicker or shorter a wire, the less resistance it has. The longer or thinner wire, the more resistance. And as you've learned in previous classes, we measure resistance in ohms. So let's throw that on the whiteboard. And we've got potential, which is our pressure, and E, voltage, EV and E. We did current a second ago with amps. And of course, we get to resistance now, which is the opposition to the flow. And it is R. But most of the time we actually would use the symbol omega for ohms, but you will occasionally see it in R, V equals IR, or E equals IR. You'll see it in those cases when it's explained in phenomena. So you will see R, but most of the time you see ohms. So take just a side note here, because you can't talk about resistance without talking about impedance. Resistance applies to direct current. But once you get into alternating current, you slide into impedance, which is a much more complicated concept. Initially, you can think of it as basically the same thing as resistance. It is the opposition against the flow of charge, specifically alternating current. And resistance is much more complicated because it has impedance is much more complicated because it doesn't just have resistance in it, but it also has inductance and capacitance, which we will talk about in later in this course. But at the moment, we're going to fold it all together and say that this impedance is a one number value of opposition to charge, in specifically to alternating current. It is measured in ohms. That simplifies it way beyond it. It's been oversimplified. Impedance is much more complicated mathematically. But the key thing to remember is that the effects of impedance, its resistance, its opposition against charge, varies with frequency. So even though it's got a single value, that single value only applies to a single frequency. Throwing it up on the whiteboard, we've got, here it is, impedance, subnote, that includes resistance, capacitance, and inductance. It is the opposition to flow, but it's AC only. It uses the letter Z, which of course is kind of interesting. And it's also measured in ohms to make things confusing. And we also, of course, use the omega. I'm going to break this video up here and start with the second half in a second here on a separate video.